Hello, everybody. Can you hear me? Okay, let's start the parallel session this morning. The first speaker is Carol Wagner. He will talk about Berengenius. Let's welcome Carlos. Hello?
I guess Carlos is not online. Maybe Jim can be the first speaker. And then we wait for this Carlos, maybe as a second.
Sure.
Okay, go ahead.
I'm happy to go ahead, but do we want to give Carlos a minute just in case he's a minute behind?
Because like a time issue.
Okay.
We can start right. Yeah, because the time is short.
Very good. I'm happy to go ahead. That sounds great. Let me go ahead and share my screen then. Hold on. Not expecting quite to be ready yet, but that's okay because I am ready. All right, so.
Okay, go ahead.
Very good. Can you see this screen? And I'm going to go full screen with it.
Yes, yeah.
Can you see it okay?
Yeah, good.
Shall I go ahead?
Okay, let's welcome Jim Harrison. He will talk about string landscape and particle remnants. Let's welcome Jim.
Thank you. Thanks to the organizers for the invitation to speak. It is wonderful to be seeing some of you virtually, even if we're not seeing each other in person. And hopefully next year, finally, we can all be together again. I'm going to tell you about the string landscape and particle remnants. This is some work that I have been involved in for a number of years now from a number of different angles. And I'd like to try to explain a little bit about what this is. I'm not going to have to say too much about computational aspects of the string landscape, but I would like to remind you that when you do something like Google string theory landscape, you see these pictures of these sort of energetic landscapes, which have many local minima, for instance, like here. And one of the difficult things in string theory is figuring out which minima are we in, and more importantly, what sorts of minima does cosmology select over, over others with some probability ratio or something like that. One wants to know the distribution on vacua. It's a very hard problem. And a basic point just to keep in mind in the back of our heads is that these sorts of questions about theories with sort of energy landscapes with many metastable minima are all over the place in science, even if they aren't quite as regularly arising in elementary particle physics. So for example, in deep learning, there's something called a loss function. And the loss function has this complicated landscape on parameter space associated with the neural network. And the goal of deep learning then to make good predictions is to be able to find low loss minima, which is sort of a deep learning analog of finding vacua in particle physics with small cosmological constants. So part of the point is that landscapes are ubiquitous, important, and hard in STEM. This is not just a string theory subject. A lot of the details have to do with string theory in the context I'll be talking about today. But generally, this sort of problem is arising in physics. For instance, also in spin glasses and in protein folding. And so computational questions naturally arise and come to the fore, which sort of begs the question, how do we think about computer science fitting in with the usual stories that we tell about math and physics and the way that math and physics have influenced each other since the Greeks. Of course, going back to Galileo and to Newton and all the way into modern day with various different interplays that happen in my string theory community between algebraic geometry and topology and physics. The usual story is that math and physics belong together, but what I think some of us are starting to get interested in is the idea that computer science is playing an increasingly important role in interfacing with physics and with math, where we're not just using computer science to better tackle physics or math, but we're actually using math and physics to understand computer science. So I like to think of this as the new kid in town. This is something some friends and I, some of whom are in the audience, are thinking a lot about these days. And the questions sort of revolve around how do the new developments in deep learning and quantum information for other people, how do those influence the ways that we're thinking about math and physics? And so there's this growing intersection of physics and machine learning that I'm really glad and honored to be a part of. For instance, we have this Institute for Artificial Intelligence and Fundamental Interactions, where we have lots of friends using deep learning for various different purposes. In my case, in many cases, it's for the string landscape, and I'll tell you about that today. But this is a growing area, and I think for the biggest questions that we face in physics in regards to landscapes, being more sophisticated about our computer science is simply a must, and there's really no way around this. So if you're interested in learning more about this, I might encourage you to check out the bi-weekly iFi colloquia that are starting on September 17th. And or alternatively, we have this wonderful virtual seminar series called Physics Meets ML that you could sign up for, or you can just reach out if you're looking for ways to connect. So this is very exciting, but it's not what I'm going to talk about in detail today. Since this is SUSY 2021, I'm not going to talk about quite as much about the computational aspects of how we understand the string landscape using computer science. Rather, I'm going to talk about, given what we know, what are the sorts of particle cosmology lessons that we might take away from what we know about the landscape. So concretely, what I want to ask today is, what are the best takeaways from the string landscape in 2021, given the various things that we know? Of course, this perspective that I'm going to present is one that's from my perspective, but I'm going to try to convince you that these things are well motivated broadly in string theory. So this talk is about string pheno in 2021, and the way that I want to address it is to ask the question: if we were to draw vacua from a uniform distribution on known string constructions, what would we find? So that's not quite the right way to phrase the question cosmologically, but it still is something. And what you would find if you drew vacua from the uniform distribution on known string constructions is that you would find many axion-like particles, many gauge sectors, and in cases where you can control the theory particularly well, due, for instance, to a supergravity approximation, those axion-like particles and gauge sectors are light and weakly coupled. And of course, those sorts of statements that I just made can have very important implications for particle physics and cosmology. So a punchline of this talk is that there are potentially detectable remnant degrees of freedom everywhere in string theory, and this can present both problems and opportunities for our hopes and dreams for what we hope to achieve in string theory. And I would point out that when I say a remnant, part of the reason that I choose that phrase is that these are particles that sometimes just arise in string constructions. They're not necessarily put in to do something. They might just be there rather than being there to solve a problem that we care about from the bottom up. For example, the way that we do with weak supersymmetry, weak scale supersymmetry, and the hierarchy problem. Okay, so I'm gonna, of course, have to be a little quick here, and I really do want to leave some time for questions. So I'm going to give you sort of a 4 or 5 slide overview of some of the things that we know about string phenomenology in 2021. The brief review is that, in case you haven't followed these things recently, is that the string theory is, of course, a quantum theory of gravity. It's a candidate theory of everything. It can give rise to semi-realistic particle physics and cosmology. And one of the central aspects of how we carry out this study is that there are extra dimensions of space, which we compactify down to 4 dimensions. And the geometry and the topology of the extra dimensions are crucial in determining the properties of the 4-dimensional physics in the low energy 4D effective theory below the Kaluza-Klein scale. So in particular, there are many ways to do this, which is often called the string landscape, which are many solutions or vacua of the theory. And this gets combinatorically large very quickly. So for example, the number of so-called Kreutzer-Skarka-Calabi threefolds, which are good manifolds to compactify string theory on, is some very large number, 10 to the large number. I think the upper bound is around 10 to the 900 currently. Alternatively, there's 10 to the 755 F-theory geometries that my group was able to actually write down an algorithm for to construct. And I'll tell you some of the properties of those. And there's a famous result due to Taylor and Wong that in a fixed geometry in F-theory, where you fix the geometry of the extra dimensions, there's 10 to the 272,000 fluxes potentially that one would be able to turn on using traditional flux counting techniques. So this is difficult. These many vacua via Coleman-DeLucia tunneling, for instance, can exhibit bubble nucleation, where one produces true vacuum out of false vacuum or nucleates from one metastable vacuum to another. And this bubble nucleation gives rise to a cosmological picture where predictions are necessarily statistical. And of course, the cosmological dynamics affects the statistics and maybe even anthropics. And this is a very hard and hairy question. So crucially, what we don't know currently, and what is a very important but very, very ambitious and perhaps too hard goal for the long term, is to figure out the right cosmological distribution on vacua. And that's exactly what we don't know now that we would love to know. So like I said, I'm going to take a different approach in this talk. I'm going to say if we drew from a uniform distribution, given what we know in 2021, what would we find? And a caveat that I should say is that the broader we go in the landscape, the fewer the details are worked out. So the way that you should think about this is in the cases that we can best control, it might be a relatively small patch of the landscape and we have exquisite control, but it's less of a broad picture. So that's a very finely detailed painting. As we go broader in the landscape, which is what I'm going to be talking about here, you should think of impressionism, not high-res photos. So I can comment on all of these caveats, but I'd like to give you a flavor of some of the things that are out there. So first of all, let me tell you about the largest known ensemble of concrete visible sectors in string compactifications to date. This is some work of Miriam Svedek and myself and Ling Lin and Muyang Lu and my former student Jiahua Tian in 2019. The result is that there are 10 to the 15 provably distinct, fully consistent compactifications of a type of string theory called F theory that exhibit the exact chiral spectrum of the minimal supersymmetric standard model. The picture is that you have a geometric construction where you have something that looks a little like this, called a reflexive polytope. You triangulate the points, and the one of these faces, it's a slightly different picture, triangulated might look something like this, and this might be another triangulated face from another side of the polytope. And this information in algebraic geometry does something called forming the base of an F theory elliptic vibration, and this specifies the F theory geometry. So the number of ways to do this for a particular class of reflexive polytopes is about 10 to the 15. There's various sorts of engineering things that cut you down by a factor of 2 or 3 from there that are important. But at the end of the day, when you try to tune 7 brane sectors to realize the MSSM, you can do it. And in fact, we're able to achieve 3 families. So there's open questions there. This is the main result of this paper, and it was a fun one. But one of the things that string theorists often emphasize, and I think it's an important thing to emphasize, is that just because we have lots of low energy effective theories does not mean that we can do whatever we want and we can tune all of the couplings to be whatever we want. Remember, in strings, our couplings are arising as the expectation values of scalar fields, and there's correlations between them. And so given any concrete construction, you can ask, can I do X without changing Y? And generally, you can't. There are constraints. So rather than go into detail about certain aspects of this, I'd like to point out that in this concrete ensemble of a quadrillion F theory standard models, we realized in a later paper that there are, I should point out, Cody Long is also on this paper. I forgot to put that down. In this follow-up paper, what we showed is that the following cannot be true, that our vacuum with the correct standard model gauge couplings lives in this or a related ensemble. 2, the theory is controlled. That is, we're in the supergravity approximation and we can ignore detailed alpha prime corrections. And 3, that there are no additional dark sectors on 7 branes. So in particular, you cannot control the theory and get the correct values of the standard model gauge couplings while having no dark sectors on 7 branes. So this is the sort of constraint that one would hope to be able to understand more broadly in string theory. But the upshot is that there really is no free lunch, and we cannot just tune the string effective field theories at will to whatever we want. So this is a very fun idea, and it motivates a number of follow-ups. But what we already know, given the structure of the geometric moduli space, is that you're not able to achieve all 3 of these things simultaneously. But I'd like to go broader than that. This is a small number in string landscape worlds. This is 10 to the 15. It's a big world. It's a bigger world out there in F theory. There's a much broader set of geometries that one might study, and there's many fluxes that one might turn on. So the result for the Calabi-Yau fourfold that supports the most number of flux vacua using traditional counting techniques is 10 to the 272,000. This is work of Taylor and Wang that I already mentioned. The result is that before fluxes, every point in the complex structure moduli space, which is a particular type of scalar field, every point in that moduli space at generic points exhibits a particular large gauge group that takes this form before taking into account the fluxes. There's also many axion-like particles in this context. So if our vacuum were one in this very, very large ensemble, what you would expect is large gauge dark sectors and axion-like particles. So cosmology would become particularly complicated. But these are many fluxes on one fixed vacuum, one fixed geometry. You can also concretely construct large ensembles of geometries. This was work from 2017 that my group did. Cody was my postdoc, and Ben currently is my student. He's applying this year. And what we have is an ensemble for constructing 10 to the 755 topologically distinct string geometries. They are all connected to one another by topological transitions in a connected moduli space. But when you, for any given one of them, compute the low energy effective theory, at least at sort of a leading impressionistic order, what we find is that there's about 750 gauge sectors in each of these different geometries, and the number of ALPS is in the thousands. So again, a slightly different context than the one on the left-hand side here, but notice that what's happening in both of these cases is that there's many degrees of freedom beyond what one would have naively ordered to solve problems from the bottom up. And one should take both these dark gauge sectors and these axion-like particles very seriously if our vacuum is arising in such a context. So this is the takeaway, that there are remnant degrees of freedom coming from string constructions. And I would say many people have talked about this sort of thing long before me. And in fact, I think this is one of the big takeaways from 35 years of string phenomenology, that there are string remnants arising in string constructions. These are new degrees of freedom that are apparent accidental consequences from the UV. They are not necessarily motivated by shortcomings of the standard models of particle physics or cosmology. So if you're into model building because there's some experiment that might probe some sort of degree of freedom, but it's not necessarily there to solve the problem, depending on the details, these are the sorts of things that can arise in string constructions. One result that at least affects how I think about things since this set of TASI lectures that Paul and I put out in 2018 is implications of control. So the largest number of vacua that I quoted before arise in cases where the extra dimensional geometries have large numbers of topological cycles. And there's a result out of the Cornell group from a few years ago that if you demand control in a canonical way that we like to study, it does something called push you out into the stretched Kähler cone. Concretely, what that means is that if you demand control, the physical implication is that these remnant degrees of freedom become more important. That is, the axion-like particles become lighter and lighter, and the gauge couplings become weaker and weaker. So in particular, if you have some dark blue ball sector arising from some dark Yang mills, the gauge couplings will be weaker and weaker in cases that you can control. And so these blue ball masses are going to be lighter and potentially more relevant cosmologically speaking. Okay. And as a final illustrative example, and I'm going to try to end with sort of 3 to 5 minutes to spare so that I can be sure to have time for questions, I'd like to tell you a little briefly about ALP photon couplings. This is a beautiful story that people have been studying in different contexts. I got into it a few years ago myself. And I think this is the sort of model narrative from string theory that I think is well motivated, at least. And this might be a model narrative for how one does string cosmology or string phenomenology in 2021. So I think these are the goal is to arrive at well-motivated ideas from string theory for phenomenology. So if string theory is true in the sense that our vacuum actually is a string vacuum, it has a photon. Everything I've told you so far says that axion-like particles are a good bet, where the number of ALPS, which henceforth I will call n, is large. In cases that we can control, a la this Cornell paper, many of the axion-like particles should be light. And in particular, no symmetry forbids a G-ALP photon-photon coupling in the effective field theory, this GA gamma-gamma. And so in principle, many axion-like particles could couple to the photon. So a question that I would love to know in much more detail in the string landscape is how does the expectation value for GA gamma-gamma scale with the number of axion-like particles in the landscape, keeping in mind that currently we think that large N is where most of the landscape lives. So this was our first try at it in a paper from 2019. We had a particular model for how we consider ALP photon couplings in actual string constructions with actual Calabi-Yau geometries. And right, so we used a computationally precise, but nonetheless toy model for the photon. One might expect that for n equals 1 for a single ALP, the coupling to the photon will be like 1 on string or something like that. or one on Planck, one on some high scale. But what we find is that as n increases, the mean of GA gamma gamma is going up with this factor n to the 1.77 or so that it's becoming increasingly detectable at large n as n increases. So this is a projected number that I can get into if it's interesting to people. But what I would point out is that as the number of, roughly as the number of axion-like particles is going up and up and up in string theory, one might expect that it's going to become increasingly common for them to couple to the photon, which might push you into regimes where they can be tested in, for example, next generation axion helioscopes, existing X-ray satellites, or next generation X-ray satellites. So this is one story that I like about how string theory has affected how I think about particle physics and cosmology. I think this is a particularly interesting direction to continue on. But this is sort of an example narrative of how one might construct stories from string theory. So just concluding, once again, string phenomenology in 2021, the basic takeaway that I'm trying to emphasize is that when you draw vacua from a uniform distribution on known string constructions, what you find is that there are many axion-like particles, many gauge sectors, and when you can control the theory in canonical ways that we know and love, those axion-like particles and gauge sectors are light and weakly coupled. In particular, potentially detectable remnant degrees of freedom are everywhere, which present both problems and opportunities. And I think at least in the context of string theory, this simply has to affect how we think about particle physics and cosmology. There's a question, which I'd be curious to hear about how this complements shifting paradigms in phenomenology in terms of what people are focusing on. But this is the message that I wanted to convey. So the general model building conclusion is that string remnants aren't there to solve a problem. They're just there, and we should take them seriously. So thanks a lot. That's all I had to say, and I left 4 minutes for questions. If there are questions.
So any questions?
I may ask?
Yes.
With this ALPS that you mentioned, can you make a statement on either the mass or the coupling by which you would say if you can reach a certain level?
Okay. Hello? 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 Can you hear me?
Unmute me. Unmute me.
Oh, it's okay.
Thank you. Yeah, you had to unmute me. Sorry, I was clicking unmute, but it said I
Okay. Yeah. Okay.
Could you repeat your question, please? I'll share my screen again. Someone had a question.
Any more questions?
let me comment a little bit on masses and coupling, since the question sort of isn't being repeated. So this was one of the big points of this paper out of the Cornell group. There is a bit of a lamppost effect here because it's sort of demanding control in a canonical way. But what they found is that when you have control in the case of large number of ALPs, the lightest ALP masses become lighter and lighter and lighter. And so what mass threshold you set as relevant depends, of course, on the application, because axion-like particles could be the inflaton, or they could be extra degrees of freedom that are important for contributing to N effective, or they could be dark matter, or they could be coupling to the visible sector. But the basic takeaway is that regardless of the application, the lightest axion-like particles are going to be becoming lighter and lighter as the number of axion-like particles goes up, which sort of changes the potential cosmological implications of that lightest axion-like particle. Sorry for the confusion about the muting. Are there any other questions?
Okay, any more questions?
Hi, I have one question.
Yes.
Okay, go ahead.
There are many vacuum, if they are all degenerate, or which one is a global one?
Good, that's a great question. So I'll go back to my first picture. The answer is we don't know. But the expectation is that there are many, many, many vacua. Indeed, one of them is probably the global minimum, but there are many, many metastable minima that, that exist. And via Coleman-de Lucia false vacuum decay, that can bubble nucleate from one vacuum to another and populate a bubble cosmology with many vacua. We don't know what the global one is. In particular, the global one should be an anti-de Sitter space. But in some sense, for the basic cosmology applications and bubble cosmologies, that's not quite the right one. The sharpest question that one would want to ask in conventional contexts is, what is the distribution of decay rates of the different vacua into one another, and how does that affect the probability distribution on vacua induced by the bubble cosmology? So it's a dynamical question. The global minimum would be interesting to know, but it's probably not relevant for the cosmological questions we want to ask. Yeah, good. So there can be, there's a question in the chat. How about the constraints on light degrees of freedom from Big Bang nucleosynthesis? So this, I think, is another fantastic takeaway from string theory generally. So I talk about this in the review with Paul. Somewhere on this table, we talk about moduli and moduli domination. And so there are indeed constraints on moduli domination via the so-called cosmological moduli problem, to be able to ensure that after sort of the lightest modulus that's relevant decays, that you reheat to above the nucleosynthesis temperature of 5 MeV. So that's an important angle also. These axion-like particles that we are considering in many applications here are much, much, much lighter than the 50 TeV scale or so that is canonical for the Big Bang nucleosynthesis constraints. Rather, the axion-like particles that are relevant for these ALP photon experiments, for instance, are all below EV scale in mass.
No more question. Okay. If no more question, let's thank James again.
Thank you all so much. Sorry for the little confusion during the question time, but I'm glad that we still had time for a few questions. If there are other questions, please feel free to send me an email. Thanks.
Okay. Okay. Carlos is still not here. Let's move to the next speaker, next talk. The next speaker is Zerkis Tata. He will talk about aspirations and prospects for natural supersymmetry. Let's welcome Zerkis.
Hi, I'm trying to share my screen. So sorry, I didn't do it in full screen. I guess I have to get out before I can make it full screen. Sorry, let me get out. Oh, sorry. No, I'm trying to share it. in the full screen mode and I don't seem to be succeeding. Can you see my screen?
Okay, it's okay. Yeah.
Yeah. Can you, just a question, can you see the pointer? I mean, that I'm making, I'm pointing a hand at Zoom. Can you see that?
Yeah, I can see it. We can see it.
Okay, great, thanks.
Okay.
Okay, thank you for having me here. I want to tell you at least my perspective on why we should still continue doing supersymmetry. And I take you back to the early 80s when supersymmetry entered particle physics. To this audience, I don't have to go through all the reasons why. I just want to highlight that the 80s were when people realized that SUSY could stabilize the electroweak hierarchy. And the bonus we got, and so that was the only reason why we expected superpartners at the TeV type scale. And the bonus, of course, when LEP measured the gauge couplings, they seem to unify in SUSY, but not in the standard model. And unfortunately, there is no sign of SUSY yet. And there's been a lot of hand-wringing over this. We have seen these plots from our experimental colleagues, and they tell us that unless the SUSY spectrum is somewhat compressed, the gluinos are 2 TeV heavier than 2 TeV. The third generation quarks are heavier than 1.2 or 1.3 TeV. For quarks, if all the quarks are degenerate, they told us that the bounds are around 1.7, 1.8 TeV. But if all this, there are 8 flavors of degenerate quarks. But remember that if there is only one light quark, the bound will be just near a TeV. And also, they treat these things flavor independently. That is not quite true. This plot has a very large gluino mass, but if the gluino mass is comparable with the quark mass, T-channel production via gluino exchange produces lots of up and down type quarks, and those will be pretty heavy. That's not shown on this plot. They also showed us that electroweak enos were not found. These reach limits look very impressive, but I think you should be careful. This is like shining a light under the lamppost. You assume something very favorable for the decay modes, and you do get very large bounds. But the really interesting bounds, in my opinion, are this purple curve on Atlas and the red curve on the right CMS plot, where the neutralino is decaying into LSP and Higgs, and the chargino decays into a W. And I think that's the interesting plot, because in these class of models, just SU2 cross U1 tells us that the neutralino coupling for the decay to Z will be very suppressed unless the spectrum is special. And Endo-san had emphasized that for this thing, that for the Higgs, W Higgs, the fact that a compressed spectrum is not yet been probed was important for G-2. There are lots of other searches also, which I'm not going to take you through. This is just, our experimental colleagues have done a very impressive job. But I should remind you that they are using simplified models, and the bounds may change under the scenario. But much more importantly, the real SUSY world as we expect it is not going to be a simplified model. And using simplified model completely ignores interrelations between various searches. And it's not important for putting bounds, but it could be very important if signals were seen. And I hope our colleagues will remember this and keep the capability of being able to do this. The latest analyses are never done in models. The LHC8 analyses, I found some particular model, specific model analyses, and I like MSUGRA, which we disfavor today, but nonetheless, we should keep in mind that this capability should not get lost. Why did SUSY solve the hierarchy problem? Well, you all know that the scalar mass square receives radiative corrections, if the standard model is, or our low energy theory is coupled to a theory with a high scale, the scalars are quadratically sensitive. That's coded in the C1 term. And then there is a logarithmic sensitivity to a high scale also. And the great thing about SUSY, or softly broken SUSY, is that the C1 term is absent. So there is no quadratic sensitivity to the high scale and only logarithmic sensitivity to a high scale. And that's how the problem is solved. The big hierarchy problem is solved, that the SUSY mass is not drawn to the high scale, but only has a weak draw to the high scale. And people used to write down things like this, just writing the SUSY term. If you take the high scale to be the gut scale, the log is around 30, 40, 50, something like 30, 40. And the 16 pi square times color factor times the log is of order 1. And so people thought that the correction to the Higgs mass, if it was to be less than the Higgs mass itself, the SUSY scale had to be comparable to the Higgs mass. And that's why people were very optimistic for seeing SUSY at LEP. And of course, that was not seen, as we all know. And in recent times, or not in recent times, for the last many years, SUSY has received a lot of bad press, not only in the actual press, but also within our community, and I think in the funding agencies in the US. So why did all this negativity come from, and is it warranted? And in fact, the absence of signals at LHC8, people actually constructed models to suppress the missing ET. Just I'll briefly point out. One is, of course, the SUSY compression of the SUSY spectrum, which we have talked about. The second is to suppress the missing ET, they made the LSP unstable. And if the LSP decayed hadronically, then there would be no extra leptons and the signal would be much harder to see. And LHC, the earlier LHC analyses exist on this. And a third way, some groups, what they tried to do was to dynamically suppress the missing ET. I don't have time to talk about that in detail, but these models went under the name of stealth SUSY, and the 8 TeV LHC analyses exist on even that. But the question that we should ask is it really necessary to hide SUSY from the LHC, or could it remain hidden? And again, I remind you, this is the same equation that I had written before of the logarithmic sensitivity to high scale, where the low scale now I've replaced by the SUSY scale. And of course, there are many such terms because groups of different superpartners will give you their own contributions. And this delta, the sensitivity that you get, say, suppose you are considering a top squark loop. This is the the Yukawa coupling of the top type Yukawa coupling, which is large. And then people saw that if you do this directly, you will get that top squarks should be smaller than a few hundred, couple of hundred, 300, 400 TeV, depending on what sensitivity you allow. And of course, the stop limits are much larger, so this was considered a problem. But of course, this is logically correct only if you believe that the top contribution and the other various contributions that come are completely independent. But that, in my view, is an absurd way of thinking, because if we understand how supersymmetry is broken, we don't understand it today, certainly there will be many correlations that are present, just as they are present in weak interaction theory in the standard model, compared with the days when we did weak interactions as 4 Fermi theories with S, V, A, P, T type of couplings. The fact that we now have a theory of how SU2 cross U1 is broken, related all these couplings, correlated them, and there are few parameters, and we understand that. So the same thing, I believe, has to happen in SUSY. If SUSY is realized, there is presumably some manner, which we don't know, in which it is broken, which will correlate these couplings. So to look at this independently, I think is a mistake. And if we do think of corrections as independent, we might end up throwing the baby out with the bathwater. So even though we don't have a compelling model today, we should not ignore these correlations. But the question is, if we don't have a model, how do we know what the correlations are and how can we play the game? And for that, our group had suggested to look at this minimization condition, which fixes the Z mass in terms of the Higgs parameters and the other SUSY parameters. This is a weak scale relation, okay? Everything is at the weak scale. These sigmas are simply finite corrections. There is no lambda in it, no cutoff scale in it. There's no m half in it. And then what we had suggested as using as a fine-tuning measure is this delta electroweak, which says that there should be no cancellations, big cancellations among these various terms. And because there are no large logs in this thing, clearly delta electroweak is going to be smaller than the usually used fine-tuning measure. I'm not saying it is a fine-tuning measure, but this quantity is going to be a bound on the fine-tuning measure, modulo some technical constraints. Now imagine that the parameters by luck now, because we don't understand, are correlated so that these large logs roughly canceled. And if they're roughly canceled, this delta, the fine-tuning measure will reduce to delta electroweak. And we have checked this in specific models. And what we suggest was therefore to use delta electroweak as a very conservative fine-tuning measure. And we allow fine-tuning between somewhere, we chose 30 arbitrarily as between 1 and 2 orders of magnitude. 1 order we thought was not enough, 2 orders seemed like fine-tuning, but I admit that is arbitrary. And so if you look at features of these models which have delta electroweak less than 30, because the Higgsino mass enters the MZ relation very directly, the Higgsino mass parameter cannot be large. The mu cannot be large. So there must be light Higgsinos. That is a generic thing. There are ways around this, but they are contrived, and I won't talk about them. So the Higgsino mass scale must be tied to the Z mass scale, and typically the delta electroweak less than 30 implies that the Higgsinos are less than about 350 GeV or so. The stops, because they enter only at the loop level through the sigmas, can be an order of magnitude heavier, which is very different from what we would have thought had we taken the stop loop as an independent thing. Bluinos only enter through the stop loops. So they're a 2-loop effect and they can be heavier still, and so on. So if this is all model dependent, why do we bother with this? And our philosophy is that if you study the phenomenology of delta electroweak less than 30 models, some of those models may actually be fine-tuned, but there might be models in there where the correlations are just right, that and the phenomenology of those models will be the same as the phenomenology of the models that we study. And the reason is because delta electroweak is fixed by the weak scale theory. So it's fixed by the particle spectrum. So any high scale theory which has the same particle spectrum will have the same delta electroweak. And the phenomenology of that theory will be the same as the phenomenology of the theory we are studying, because the phenomenology largely depends only on the superparticle masses. Details might not be true, and cosmological things may not be true, but the collider phenomenology will be largely determined by the masses. So the broad brush phenomenology, as I said, there'll be 4 light Higgsino states. The gauginos, the electroweak gauginos, generically would be heavy. But if they are also happen to be light, there will be there'll be large mixings between them, and the gaugino, Higgsino signals, there would be lots and lots of signals, and I think this sector would be very easy to see. So the difficult case is where the gaugino masses are heavy. In that case, the Higgsinos are still light, but the splittings are tiny, maybe few GeV. And so the spectrum is automatically very compressed. And even though the cross-section might be in the picobarn range for producing Higsinos, the signals will be way below the backgrounds. So we'll talk about the monojet and monophoton signals shortly. And then the other possibility is, if you're lucky, you might see gluinos. But the gluinos are not guaranteed to be light. So, and at the LHC, high Lumi LHC, we did a study, and with fairly generous aggressive assumptions of what might be seen. And even then, we found that the best you can do is about 2.8 TeV. And remember that the gluinos could be as heavy as 6 TeV for delta electroweak, less than 30. So how about the light Higgs-Zenos? As we said, the problem is, so people said that, okay, if you can't see pair production of light Higgs-Zenos, consider production of light Higgs-Zenos in association with a jet, say a monojet signal. And the Higgs-Zenos, because they decay only into soft stuff, which is almost invisible, will act like missing ET. And people did analyses, and they found that a statistical significance of 5 sigma was possible. But the signal to background ratio after the aggressive cuts that were needed was at the percent level or below a percent level. And since these are QCD backgrounds, probably systematics will be a problem to extract the signal. And so that's something that we should worry about, that even though signal over root background might be bigger than 5 sigma or bigger than 5, the signal to background, if it is a sub percent, you really have to be able to calculate your backgrounds at that level. And that, I think, is going to be tough. So some people had suggested that, okay, you can trigger a monojet, use the monojet to trigger the event, and then let the neutralino decay into very soft leptons, which you will be able to see to help cut down the background. And, oops, sorry. People did such analysis, and they found, yes, indeed, you could see a signal out at the high Lumi LHC to for a Higgs-Zeno mass in excess of a couple of 100 GeV. This analysis used a fairly conservative B tagging efficiency. B tagging efficiencies have become better, and the signal, in fact, might be seen out to even larger values. But this analysis was done in what is called a non-universal Higgs mass model with Higgs-Zeno mass unification, where the splitting of the neutralinos is guaranteed to be bigger than 10 GeV. Now, if the splitting becomes even smaller, the leptons become even softer, and the signal will be hard to see. So the crucial question is, how low a delta M can you cover? And luckily, our experimental friends have been looking at these analyses, and they have shown exclusion plots, like on the left by Atlas in the delta M and the neutralino mass plane. And this is the right side is from CMS. And what you see, two takeaways are that they have bounds, and the bounds are going up to almost a couple of 100 GeV for the optimal delta M. That's not the discovery reach, it's a bound. But more important, that they can go down to fairly small delta Ms, although, of course, the bounds become weaker. So it's going to be very important to see how well you can cover this region, as we'll see shortly. And right now, our group is looking at a different set of cuts than are traditionally been suggested to reduce the Z to tau tau background. And we have some positive results, which I don't have time to talk about. If there are light Higgs-Zenos, there is another very characteristic signal that can happen. And that is if you are lucky enough that you can also produce the Higgs-Zenos, electroweak Higgs-Zenos, the Venos. Because imagine you produce a neutral Veno and a charged Veno. Say the charged Veno is positive, and so it decays into a positive W. That happens almost 100% of the time, or with a large branching fraction. The neutral Veno can go equally likely into a positive W or a negative W, and a Higgs-Zeno. These Higgs-Zenos, as I told you, have very soft decay products, so they are invisible. And so you get two same sign Ws. And when these Ws decay leptonically, you see two same sign leptons, for which the standard model background is very small. And there is no QCD radiation. So such events will be very characteristic, and people had studied them, and they find a pretty good reach. Unfortunately, this plot is very small. So here I've shown this in the non-universal Higgs mass model in the M1/2 plane on the horizontal, and the mu, the Higgsino mass on the vertical. And below this line, at the high Lumi LHC, below this horizontal blue line, you can see the dilepton signal, the soft dilepton signal with monojets. To the left of this line, the signal, the same sign, W signal is guaranteed. So in this region out here, you're guaranteed to see a signal at the high Lumi LHC. And here is a contour of delta electroweak less than 30. So what you see is the confluence of these two signals at the high Lumi LHC would cover most of the natural, what I call the natural region. But of course, this depends on the gaugino mass unification. And gaugino mass unification may not be true. In that case, of course, we'll need other colliders. And at an E plus E minus collider, with a 600 GeV center of mass energy, such a collider may never exist. But if you had such a collider, you would be guaranteed a signal for Higgsinos. This is, I'm running out of time, so I'll skip over this slide. This is to just tell you that there are a whole bunch of UV motivated models where the gaugino mass unification need not occur. So what would we do then? Well, in that, if there was no 600 GeV plus E minus collider, we would look for LHC upgrades. And since CERN was considering a plan for LHC upgrades, and they had talked about a 27 TeV upgrade of the LHC in the left tunnel, we said, let's look for stop and gluino events, since stops may be light, relatively light. And this picture, this is in the gluino, stop gluino mass plane. The various dots are these various models which have no gaugino mass unification. Or some of them have gaugino mass unification, some of them don't. Okay, and every one of these dots corresponds to delta electroweak less than 30. Now, these horizontal line, this green horizontal line is below this line, a gluino signal is guaranteed to be seen at 5 sigma at LHC 27. And similarly to the left of this line, a stop signal is guaranteed to be seen at LHC 27. So what you see is all these dots either fall below the green horizontal line or the stop vertical line. So LHC 27 would be a fail-safe machine if it had 15 inverse femtobarns to see all the delta electroweak less than 30 models. And Tauhan et al. Did a similar analysis for the gluino and squark reaches. Their cuts were a little softer than ours, and they find slightly smaller reaches. We got 5.5 or so for the gluino, they got 4.7, and we got 3.1 or something for the stop, 3.2 maybe, and they got 2.8. So LHC 27 would have been a good machine. Unfortunately, this doesn't seem to be in the latest CERN plans. And they only talk about 100 TeV machine. But of course, if LHC 27 can see it, 100 TeV machine would see it, and of course would see many more states associated with the picture. So I hope I've convinced you that natural models defined the way I have defined naturalness will be seen at LHC upgrades or at a collider. Now I'm a little short of time, so I just wanted to mention that I've taken up a bottom-up view of naturalness. Howie Bayer and their collaborators, I'm not involved with this study, take a stringy view of naturalness. I put this slide in, but now since Howie has given a talk on it, a plenary talk, I can skip over it. I'll just tell you the results. So what they claim, they have an anthropic argument, which actually tells you that delta electroweak less than 30 follows from that argument. And the argument is based on the fact that the weak scale cannot be more than 4 times the observed value. So the Z boson mass could not be much more than 4 or 5 times its observed value. Otherwise, nuclei would not form. They use that result. And then they claim, this is of course a post-diction, that the most likely value of the Higgs mass is around 125 GeV, and the most likely values of the super partner masses are in this range. And Howie pushes this a lot. Assessing this is, so he says he knows now why the LHC has not seen supersymmetry. Assessing this is beyond my pay grade, and I'll let you look at his talk. So let me end with some remarks. I think from my bottom-up perspective, it is certainly possible that even in the MSSM, natural supersymmetry remains hidden from LHC searches. And we should, I mean, the dismay and the optimism that we had was, earlier was because we had not carefully looked at what naturalness meant. Specifically, we had not allowed in our considerations the possibility that the superpartner spectrum will be maybe very correlated. I'm not saying that we know the right model of how SUSY is broken and how these correlations come about, but such a possibility is certainly there. And I'll just remark that, for example, the usual fine-tuning measure from Barbieri and Giudice, we have examples where that measure will say that you have a tuning to a part in 3000, but the delta electroweak measure for the same model is less than 30. So it really makes a difference. If you believe this delta electroweak less than 30 story, light Higgs seem to be the best bet for naturalness. And they might yield novel signals at the LHC, including the same sign boson signal that I talked about. You really need a high Lumi for that, and the monojet signal with soft dileptons. And I hope our experimental colleagues will push to see the smallest splittings that they can in this channel. A 600 GeV electron-positron collider or a 27 TeV hadron collider with 15 inverse femtobarns would, of course, probe this delta electroweak less than 30, I think. And a 100 TeV collider, of course, would discover much more. So I think that our original hopes and aspirations that we had from the time that I started doing SUSY phenomenology in the early 80s really remain unchanged. We have to accept that accidental cancellations, a few percent may happen. Like pi square minus 9 occurs in the width of positronium, the decay rate of positronium. And if pi square were equal to 9, that rate would be 0. So such cancellations do accidentally happen. And we have to accept that dark matter may be multi-component. The Higgsinos, light Higgsinos cannot be all the dark matter because they would annihilate too efficiently. But if delta electroweak were less than 30, even there could be maybe 10% of the dark matter or a little less than that. And that amount will be detectable at the upgrades of xenon, the multi-ton xenon. So I still think that weak scale supersymmetry remains a good resolution of the hierarchy problem, and it offers us the best prospects for writing down theories which we can extend up to very high scales. And even with the MSSM spectrum at the weak scale, I think there can still be viable models for our experimental colleagues to find. Thank you very much.
Okay, thank Xerxes. Questions?
I'm sorry, I went over very fast, but if there is something, we can go back.
Okay. Okay, if no question, let's think Xerxes again. Okay. Now let's move to the next talk. Okay, Carlos is still not here. Let's move to the next talk. is Chauba Bullish. The title of the talk is Gambit, the global and the modular beyond the standard model inference talks. Okay, welcome.
Thank you. Can you hear me and see my screen?
Yeah, I can hear. Yeah.
Excellent. So I'm going to give an update on Gambit, the global and modular beyond the standard model inference tool on behalf of the Gambit community, which I'm also going to introduce. And the talk is going to be relatively simple, so I will just talk a little bit about global fits, and then I will talk about various aspects of Gambit. Now, so global fitting is very closely connected to what we heard already in the previous two talks, because basically one of the great questions is that whether string theory is there, if it's there, which vacuum we live in, and then for SUSY, it's a question whether SUSY is there and whether it's the minimal model or some more elaborate model. And these questions are related to this, what's the next standard model after the present one? And then the answer to that, the generic answer is relatively simple. The simplest theory, which is going to best fit the most data, will become the next standard model. However, to answer this question is very complicated because one has to quantify the simplest, the best, and the most. Simplest data, the best fitting, and most data, simplest theory, best fitting to the most data. And that's basically what global fitting is trying to do. So the center of this global fitting is this likelihood function, which is built from the theory side. So the theory gives predictions, and then those are fed into the likelihood function. And then the experiment, of course, measures data. And then in the likelihood function, the predictions and the data sort of being compared to each other, and models that don't predict very well, their parameter regions will be sort of ruled out, and then their p-value and various other model testing parameters will be low. So those models will be deemed to be sort of bad if they don't fit the data very well. And then finally, this likelihood function will allow us to compare models to each other, which one is the better model, because that's the way we can select basically the next standard model, the next best model. So the global fitting has these various standard steps, establishing some model hierarchy, going from Lagrangian to spectrum, going from spectrum to observable, and then sampling the parameter space of the theory, and then inferring basically the goodness of the model. And this is actually challenging when one is trying to do it sort of for many models, because the problem is that at this point we have many competing models. There are some more complete and less complete models, and there are some more abstract and less so high energy and low energy models, but they are still competing, and we have to sort them out. Sort the hierarchy of the models out, and I will actually show examples what this means. Then we have to be able to go from model to pseudo observables like spectra, and we have to do this fast, efficiently, and we have to do this for any type of models. And we have to have very fast calculation of observables, because the next step is to scan parameter spaces, to sample parameter spaces for all the observables, and this can take millions and literally actually nowadays billions of samples. And if you want to calculate observables in a billion places, you have to be really fast. And at the end, once you did that sampling, you have to draw some rigorous, meaningful statistical inference. And those of us who have been in the business for a couple of decades, we realize that for all models, this is basically the same recipe. and you just write a code for a inference like this, and then for your next model you write another code and yet another code, and at the end of the day you realize that the best approach to this is a code which can recycle the most. In other words, many of these steps and challenges can be tackled model independently even before you do any inference. And the best way to do this is to create a tool which is the least model independent and most recyclable. And this is why we created Gambit. So Gambit is a global fitting framework which is very modular and flexible, and these are the keywords for this model independence and recyclability. And it contains a lot of beyond the standard model models from particle physics, cosmology, astroparticle physics, and nuclear physics and beyond. And it already has a built-in sophisticated statistical inference engine and many plug-and-play tools to calculate observables. So the major reference came out about 4 years ago. And as I told you, so Gambit is designed to allow easy definition of new models, and I will come back to that, what this means, and observables and likelihoods. So it has a framework, sort of model-independent framework, and then you can sort of plug the model into that framework that you want to analyze. It has already an existing extensive model database. It has numerous observable calculators already and data libraries from experiments. So you don't have to go to a particular experiment and then start collecting data from papers if you want to compare to them. It already has the statistical engine armed with sampling tools and various pre-coded statistical options, and it has very fast likelihood calculations due to mostly the massively parallel nature of Gambits. I will tell you a little bit more details about this. This is some of the names of the people in the Gambit community. So now the Gambit community is about 70 people. So this is about 45 names. So there are actually more of us than what is listed here. What is listed here is the names which appeared on the latest papers. And this is sort of the graphical representation of us, or the part of us. This is also only about 30 of us. Whose faces appear actually on the Gambit page. The Gambit community comes from 11 experiments, and these are very familiar to you from particle physics, astroparticle physics. And then we are members of 14 major theory codes. We are actually authors of 14 major theory codes. So a few features of Gambit to just sort of tease you what this modularity and flexibility and recyclability means. So we already have a pre-coded model database, and this has to be done by hand. There is at the moment there's no better way around it. And already we have supersymmetric models, extended Higgs doublets, effective models, various models for axions and so on, and various cosmological models coded there. There are due to this database and due to the plug and play nature of the model of the code, you can actually change model assumptions without getting into the code and then starting rewriting code itself, because you can actually plug and play stuff. And so in the input file, you will tell the model assumptions, and then it will propagate down. I will also tell you how this is possible. We have a very sophisticated composite likelihood in the middle of Gambit, which allows you consistent combination of searches and uncertainties and so on. We have many built-in experimental likelihoods, as I said, and many sophisticated sampling algorithms. We have what we call it the auto dependency resolution, and I will come back to this because this is going to make your life very, very easy. This is one of the reasons why sort of Gambit is advantageous to use against compared to anything else today. And then Gambit is very fast because at this point we can take advantage of MPI and OpenMPI at the same time. So Gambit is easily running on about 10,000 or even 100,000 cores actually easily. And then now we are working on the third layer of parallelistic execution when you can actually do this 10 or 100,000 cores and a bunch of GPUs at the same time. So the features are going on and on. Let me see, pick a few interesting ones. So we backended a lot of, we interfaced a lot of existing theory tools, and then you can just turn on. You can just turn them on and off from the input files. So you never actually have to download and configure and link another or compile another theory tool again. If you do this, you can do this from Gambit. And then you can, once basically you have all those at your fingertips, you can just you can switch between them very easily. This is of course done in multiple languages, and we have sort of semi-automated interface structures within these 4 languages, and we are actually working on some more. BOSS is one of them. So BOSS is basically the C++ automated interface. BOSS can actually go and generate automatically a Gambit interface to your C++ code. So basically, we don't sit down and interface your code by hand. We just allow BOSS to generate all the Gambit submodules that are needed for the particular code, link them automatically to Gambit, and then bang, your C++ code is backended, is interfaced to the structure. So I think at this point I will show you this. This is the generic structure of Gambit, where basically the core is something like a so the core is something like a conductor. It's overlooking everything. It's communicating with the models. It knows how to deal with and select among models. It knows it governs the model hierarchy, which is encoded in these models. I will tell you more details about this. It is talking to the physical modules, and I will actually tell you about a little bit more what these are. But these are the sort of model-independent physical structures which do everything that you can do model independently for the given particular subfield of physics. You can see here the spectrum, collider, decay, dark matter, and so on, flavor type of modules. And the core talks to the samplers through another module which is called the scanner bit, and the scanner bit actually directly talks to, just like the physics modules talk directly to backends, which are model-specific observable calculators. Scanner bit talks to specific samplers. And so the core basically oversees the whole process and goes from model selection through model-independent observable calculation to calling backends, which supply effectively the observable calculation, and then instructs the samplers to scan the model. So the model database. So the models, we are talking about here parametric models. So the models are defined by the parameters and relations to each other within Gambit. Of course, the model is still, if you think about particle physics model is still just Lagrangian, but Gambit is going to know relationships between Lagrangians, and I will show you in a moment what that means. Within this relationship, you can talk about daughter models and parent models, and these models can inherit from each other, which is going to make the observable calculation much more transparent. I will tell you examples for this. So the database at this point includes several models, and this is the part of Gambit we have to code the most of. And the rest of the code, other than the modules, basically lots of things are happening automatically. So for example, here is a really simple model relationship. Recently we wrote a few papers on axions, and this is the existing model 3 within Gambit about axions. So you see that the general axion-like particles split into two, the actual axion, in this case QCD axion, and then the generic basically axion-like particle, and then the QCD axion splits into 3 different kinds. And the importance of this is that if you can lay your hand on a, let's say, observable calculator or spectrum calculator, which can do everything, which can do a particular observable, for example, for general axion type models, and then you want to do a global fit, or you want to do some phenomenology for a DFSZ axion 1 model, then Gambit will immediately know that through this model hierarchy that it can use specific observable calculators and spectrum calculators and so on for this type of model. So these model hierarchies, here is the one for MSSM, which is encoded in Gambit, are extremely important because basically they will allow you they will actually allow Gambit to survey what it can calculate and what it cannot calculate. And it can calculate a lot of things for specific models as long as the parent model's observable calculation is there. And if they cannot, then they will either tell the user, or you have an option of trying Gambit 2, which I will come to in a moment. So there are various physics models, modules, which play a very important role in this whole calculation. So this is the part of the code which I referred to already as recyclable. So these are the parts of the calculations which you would do for any model. For example, Collider knows how to go from parton level collisions to jets, and that you can do it once and for all, and Collider does it, and you don't have to redo it for each model. So basically, literally, as long as there's nothing funny going on in your model, and if something funny is going on, then you have to change Collider. But if it's just the usual bread and butter Collider physics, then you will not even have to think about it because it's already coded in Gambit. And as long as you supply the parton level collisions for your particular model, then it will take it through the LHC, it will take it through Atlas, CMS, or several actually other colliders at this point. And this structure exists for dark matter, for decays, for flavor, for precision, for spectrum calculation, which, by the way, is one of the most challenging, because basically you have to make sure that you can generate spectrum for an arbitrary model, which means using spectrum generator generators, and then this is a time order listing. So the scanner bit I already mentioned, but recently we added neutrinos, and then cosmology, and then GAM, which I will come back to that. It's sort of a highly automated generation of spectrum interface and observables. So at the backend level, we have these observable calculators. Of course, without this, nothing can be calculated, because so far we only had basically model independent stuff other than the model database, which was of course model dependent. But the modules have to call actually calculators which can calculate model dependent information once the core instructed them using the model database to do so. And so at this point we interfaced more than 24 various various observable calculators, and you notice that many of them, Dark SUSY, Sarah, LabGraph, and I could pick several ones, can do many different models. So this is the way basically Gambit is attacking global fitting and model inference and then model comparison. And this is how it's only possible. And these observable calculators range from astrophysics, some cosmology, particle physics, astroparticle physics, and actually even sort of beyond some nuclear physics stuff. So if you ran Gambit, basically you would specify some output, what you want to do, and then Gambit would build this dependency tree based on some graph theory method to optimize the calculation in every sense. So Gambit has to decide whether it can do the calculation, whether it can calculate the particular observable or observables that you want, whether it has access already to particular experiments that these observables have to be compared to, and so on. And finally, but not least, Gambit actually orders these calculations in terms of how long they take eventually. And then it starts with the fastest ones. And if it sees that the model fails already the plausibility at the fastest level, then it doesn't even go further, calculating very time-consuming observables. So this is the way to do a really fast global fit again, because for low likelihood points, Gambit hardly calculates anything. And then as it goes and finds the highest likelihoods, then it goes and calculates more and more elaborate and time-consuming observables. So these dependency trees can be quite complicated. So the one that you saw there was a simple Wilson coefficient fitting. This is a dependency tree which is once again built automatically by Gambit, and this decides, in which order and which relationships exist within, and which order the execution goes. This is for the constrained MSSM, and this is only part of that full dependency resolution. That the full dependency resolution is too detailed to show. In the background, you see all those lines. There are hundreds and maybe thousands of connections here. But each part of the dependency tree actually does its own work. So some has to do with model parameter translations. Some big clump is sorting out the precision calculations in this particular model. Large part is concentrated on colliders, of course, for supersymmetric particles. That's traditionally the case. And then the dark matter observables take precedence in this case, and flavor observables. So the typical constraints that you would impose on these models. And basically, once again, the huge advantage of Gambit is that in the old days, you or your graduate student or your postdoc had to know all this. You had to actually connect all these things, all these various aspects by hand, either within a code or within your hand first, and then in your mathematical notebook and so on. And Gambit here does it for you in 2 seconds. Basically, it just organizes the whole calculation. It decides what can it calculate. It decides how to calculate things. It decides in what order to calculate things, and so on. And it maps out all the constraints at once. And each of these small blobs is actually quite complicated. So if you had to do this every time for every model, for every paper, for every project, then you would spend your time forever doing this, while once again Gambit does it in seconds. So Gambit 2 is something that we are quite proud of. It's a recent paper out. It's just under refereeing, and Gambit 2 does sort of for the first time the dream which I envisioned when I designed the Gambit logo. It goes from likelihood to Lagrangian automatically. And so what that means is that it actually auto-generates code for the missing parts and pieces which are not already there in this whole complicated chain of calculations. And not just that, but it auto-generates the missing code and then automatically interfaces to Gambit. So basically it seamlessly goes from Lagrangian to the final likelihood, and if you want, global fit observables and likelihood and global fit. So you input Lagrangian in various forms, and then GOM, this is Gambit Universal Model Machine, is going to generate the Gambit model, the collider, dark matter and decay and spectrum code and so on automatically, and it writes C++ interfaces to the various existing modules and backends. And so basically you never actually see this, or you never actually write the code yourself. You never actually implement a model in Gambit, but it is even that is done for you. And in this paper, we show an example where we had using GOM, we had the Majorel fermion dark matter model to Gambit and the scalar mediator for that for this dark matter particle, and then do the global fit automatically. So basically, the way GOM fits into this whole structure is the following: that basically there was a sort of a hard-coded connection between models and physics modules before. This is sort of once again the map of Gambit 1, version 1. And then within here, we actually implemented GOM, which has the whole complexity of Gambit in itself. So this is what GOM does, going from models to module functions. So down here, these are the modules which you have seen. And so basically the models feed into the GOM via the Lagrangian. So obviously the Lagrangian is talking to the Gambit model database. And then the Lagrangian can take the root of Fenrose or Serra, which auto-generates, of course, interfaces, model files for NetGraph, CAGCAPS, Pheno, and Vivacious. And then once these model files exist, then these particular codes can actually calculate various observables, automated, of course, by themselves. And then they can actually talk to various modules, collider bit, dark bit, decay bit, and spec bit. And so then this can be pushed further. At this point, these modules are going to make use of the pre-generated observable calculators, and then they link them to themselves, and then they just use them as backends. So basically, the calculation at this point is miraculously automated. So using Gambit, we already created a lot of physics results. So here is, I think, a dozen physics papers listed. And now you are beginning to see why and how this is possible. So basically, we can easily switch. We can easily go from SUSY, various SUSY models, and scalar dark matter models, and various other scalar dark matter models with other spins, and then back to SUSY, and then look at axion-like particles and right-handed neutrinos, the flavor EFTs, and then generic ALP models, neutrinos playing role in cosmology, and then most recent paper is dark matter EFT paper. So this is, I'm not going to talk here about detailed Gambit results due to a limitation of time, but I just want to point out one more feature of Gambit. So you have all been there when you read a paper, you gave the paper to your student, and then you told the student to reproduce the paper, and it took half a year when the student reproduced the paper. To reproduce anything in these very, very complex Gambit papers takes about 5 minutes, because you just go to Zenodo, all the parameter point samples are there, all the input files and code is there for all the scans, and all the output is, of course, this parameter point sample. So the input and output is already there, and then the plotting routines are there. So basically your student just have to run the plotting routine on this particular output, and then bang, the result is reproduced. And then you can, if you want to understand details, you can take a more detailed look in the output, you can take a more detailed look in the input, or you can just run it through the existing Gambit code, and then you can debug it at every step, and you can actually see what happened down to numbers in these runs. So yes.
Okay.
Was there a question or?
2 minutes. Go ahead.
Okay. Yeah, I am quite on time. So actually, I'm finishing up. I just want to give sort of a preview what is happening within Gambit. So basically, more of what you have seen. We are adding more models. We are working on adding more observable calculations, making sure that Gambit 2 or GAM can deal with the most curved balls you can throw at it, which will of course mean more automation. We are including more experimental data, more sophisticated statistics, and so on. Obviously, we are trying to improve many things, amongst others speed, and machine learning seems to be a good way of doing it. So machine learning is already a part of Gambit, although it's not part of the public Gambit yet. But we are learning using machine learning on several fronts. The most obvious is machine learning cross sections and cosmic ray fluxes, and then speeding up tedious sampling, like sampling of the LHC cross sections. If you think about that, orders of magnitude. This is really very important for us, because if you have to think about it, let's say you just want to sample a parameter space and you just want to collect 1 million samples, which is nothing, because for the Zenodo databases, in some cases we have tens of millions of samples. If you want to generate 1 million samples in the parameter space, and then at every point you want to know collider cross sections, then at every point you have to generate about 100,000 collider events. So then if you take 10 to the 6 and you multiply by 10 to the 5, you are somewhere around 10 to the 11, that many collider events you have to generate, which is a lot. So basically you want to go around that, because your calculation, if you want your calculation to finish in the lifetime of the universe, you have to improve it one way or other, and machine learning is going to be one of the ways to do this. And then, of course, at the shorter term, we are actually just putting things on GPUs. Talking about colliders, another standalone unit is coming out of Gambit, which is going to be a collider with Solo, which is a really fast collider analysis of various models. This is just itself, just colliders, nothing else. And then we are working on many different papers, focusing on, obviously, many of us interested in light SUSY, various extensions of the Higgs sector, dark matter related and neutrino related projects. Axions are hot, so we are working on them, laptop works and several other things. So in summary, global fitting is really the way to find out the next standard model. And Gambit is an open source tool for that. We are trying to make it as flexible and modular as possible so that it can actually do the global fitting. It can deal with the challenges of global fitting. GOM, which is effectively Gambit 2, is that significantly enhances the capabilities of Gambit in the sense that the user now can go from Lagrangian to observables, and if they like from observables to likelihood, and if they like from likelihood to global fit, just pushing buttons and not writing actually code, which is very exciting for all of us to think about. And you have seen a sample of Gambit papers, and more is coming. So if you want to know more about specific aspects of Gambit and you want to see results in more detail, then I refer you to these four talks, which were given unfortunately earlier than my talk is. But each of these talks talk about very recent Gambit developments. So please take a look at them. And thank you for your attention.
Okay, thank you, Chaba. Any question? Okay.
Hello?
Yeah,
Hello?
go ahead. Yeah.
In order to use Gambit, which platform, computer platform is needed? There is a Mac, Windows, Unix.
Yes, so we actually have on the Gambit page, we have what we call a collider matrix. So let me show you the collider matrix. So that matrix is going to that matrix is going to decide, of course, what can you use. So basically, the short answer is that any of those machines can run Gambit. If you have an Intel GCC compiler, then basically Gambit is going to run on the ones which are ticked here. So in the Gambit collaboration, which is community, which is about 70 people, we have all types of machines. You will probably not believe this, but I'm actually using Windows, and I'm maybe the only person in the world who is running Gambit on Windows, but it's very smoothly running on Linux and on Mac.
Maybe Mac and Unix is okay.
Yes, it works on many people in the Gambit collaboration on Mac, and Linux is really the bread and butter, so that it should run on Linux.
And how good CPU is needed? More than 5 gigahertz?
So you can run Gambit on an average laptop, but
Okay, on the
you
average
will-
laptop, recent laptop.
yes, you can run it on a laptop. You can compile and run it on a laptop, but you can run it for probably one point in the parameter space. If you want to do a global fit, then you will either need a big desktop machine. So we actually run Gambit on machines with 100 CPUs. Because now you can buy desktop machines with 100 CPUs. And we actually do simple global fits on machines like that. And if you want to do an ambitious global fit, like CMSSM and these sort of things, then you essentially need a supercomputer.
Okay, I understand.
Can you discuss later? Okay, we have one more talk. Okay.
Thank you.
SUSY2021. We have one more talk is Carlos Wagner, who will talk about the barrengens. Let's welcome Carlos.
Okay, thank you very much. First, I have to apologize for the confusion. Then I thought that my talk was tomorrow and not today. So I hope you can see my talk now. Very good. So therefore, I will have to skip some slides that I was prepared to arrange tomorrow. So I will talk about baryogenesis and new physics. So let me tell you what is the problem of baryogenesis. We have the puzzle of the matter-antimatter asymmetry, namely that antimatter is governed by the same interactions as matter, but the observable universe is composed of only matter. Antimatter actually is only seen in cosmic rays and particle physics accelerators, and the rays observed in cosmic rays is consistent with just the secondary emission of antiprotons that is about 10 to minus 4. So we have a problem. So because baryons annihilates with antibaryons with strong interactions, they are mediated by mesons. This is a very efficient process. And actually, if you start with equal numbers of baryons and antibaryons and you let them annihilate, you will end up with a ratio of baryons to photons of about 10 to minus 20, and the same will happen with antibaryons. And this compares badly with experiments. First of all, we had the problem of the asymmetry between matter and antimatter. And second, from the analysis of the Big Bang nucleosynthesis and cosmic microwave background radiation, one obtains that these ratios to be of order 6 times 10 to minus 10. So actually, this baryon abundance in the universe is very well known, as I said, by these two methods. So one BBN gives us the ratio of baryons to photons. Cosmic microwave background radiation gives essentially information about omega baryon, the ratio of the baryon energy density to the critical energy density. The two are related, then due to the fact that each baryon weighs approximately 0.94 GeV, and that is the relation that is given by the two expressions. And as I said, I can obtain information on eta, the ratio of MB over M photons in the universe, and of omega B by analyzing Big Bang nucleosynthesis and CMB. And both methods give consistent values that are about 6 times 10 to minus 10. So the question is how to explain the absence of antimatter and the appearance of such a small asymmetry. And the easiest way of doing is that this small asymmetry may generate dynamically at temperatures below the reheating one, but above the nucleosynthesis one, by a process of a small asymmetry, a small CP asymmetry that appears. And then we have the great annihilation, and from this, so 10 to the 10 baryons and antibaryons, when we have this annihilation, we end up with simply this asymmetry of baryons compared to antibaryons. So that is the way we think about baryogenesis. So we have to generate this small asymmetry between baryons and antibaryons in the primordial universe. So under natural assumptions that includes CPT conservation, there are three conditions enunciated by Sakharov that need to be fulfilled for baryogenesis, and the standard model, amazing enough, fulfills them in certain conditions. So we need baryon number violation, obviously, to generate baryon number. We need C and CP violation to generate the asymmetry between baryons and antibaryons. And we need non-equilibrium processes that in the standard model would be possible at the electrolyte phase transition. Now, baryon number violation in the standard model occurs via so-called Faleron processes. So we know that if you study the space configuration, the field space configuration, so we see that there are different vacuums, different baryon numbers that are separated by a big barrier. This barrier is controlled by a height that is proportional to the so-called Faleron energy, that is proportional to the vacuum expectation value of the Higgs, inversely proportional to the gauge couplings. And if we compute, if we can go from one vacuum to the other, so then we have a violation of baryon number and lepton number by 3 units, but B minus L, as we know, is conserved by these instanton-like processes. So if we go to final temperature, so then we see that the extremely suppressed processes at 0 temperature that we know that are very suppressed by the instanton action that is proportional to 1 over alpha weak. So at final temperature, they are only Boltzmann suppressed, and the Boltzmann suppression is proportional to the height of barrier to its Faleron energy. So if we are at temperatures below the electrolyte scale, where the vacuum expectation value of the Higgs develops, and if we are at temperatures above the electrolyte scale, so we have that this baryon B plus L violation processes are proportional to T to the 4th. So, and these Faleron processes, these B and L violating processes that conserve B minus L are very important. And let me give you an example, the relevance Faleron processes in the case of SU5. Imagine that I want to generate the asymmetry between baryons and antibaryons via the case of the extra gauge bosons that appear at the granification scale. There's that 12 gauge boson. In particular, there is a gauge boson X that couples like a leptoquark to lepton and to quarks in the process that I show here. So then I also can produce pairs of quarks. So now if I analyze a branching fraction for the decay of this gauge boson, I obtain that if the decay into quarks is equal to R, the decay into quarks and lepton-quark process is equal to 1 minus R. And in one case, you generate a baryon number that is 2/3, in the other, you generate a baryon number that is minus 1/3, just from the quantum numbers. And the same happens with the antiparticle, but with the opposite quantum numbers. So the idea is that the decay process of anti-X into pairs of quarks is different from the X decay into a pair of quarks. So then R is different from R bar, and therefore I have these famous CP violating processes. If I compute the net baryon number that is obtained from the case of X and X bar, so then I compute the B that is obtained from the case of X, the B that is obtained by X bar, I add them up, I have the total baryon asymmetry obtained that as expected is proportional to R minus R bar. And the same happens with the lepton number. You can compute the lepton number that is produced from the decay of the heavy gauge bosons, again obtain that is proportional to R minus R bar by the same calculation, similar calculation. Now, what happens with Falerons? Faleron processes are in thermal equilibrium at high energies, high temperatures. Since they violate B plus L, the Faleron processes will try to suppress B plus L. So we try to generate B plus L equal to 0. But since the Faleron processes, since the processes that obtain conserve B minus L, so B minus L from the beginning is equal to 0. Observe that the B and L indeed are obtained such that B minus L is preserved. But since B plus L tends to be erased, B plus L is equal to 0. So that means that and B minus L is equal to 0, I obtain that 2B is equal to 0, meaning that B is equal to 0. So the generated baryon number is totally erased. So Gabriel genesis in SU5 or any other B minus L preserving gas theory doesn't work, and I need to break B minus L. And there is where the idea of leptogenesis, there are many ways of working, breaking B minus L, but leptogenesis is one particular attractive one. So in this case, the baryon asymmetry is generated by generating just a lepton asymmetry, and we let the B minus L, B plus L evaluating processes to act. So the following process to generate a given baryon asymmetry. So lepton number relation is naturally associated with heavy Majorana right-handed neutrinos. Such particles can both explain the smallness of the subneutrino masses via the SISO mechanism and lead to a necessary generation of lepton number via the decay of Majorana neutrinos. And let me specify how this works. The SISO mechanism, as you know, is generated by simply Yukawa couplings of the Higgs to the standard leptons and a heavy Majorana neutrino. This heavy Majorana neutrino is characterized by this mass M, and if M is sufficiently large, when I decouple the heavy Majorana neutrinos, I get an effective mass for the light neutrino that is proportional to the square of the Yukawa coupling, square of the Higgs vacuum expectation value, but inversely proportional to the heavy Majorana mass. And these are Majorana masses. That is very important. Now, what about lepton number generation? Well, I have the decay of the heavy neutrinos, N1 and N1 bar. So actually, both of them, since our Majorana can decay both into lepton and antileptons, and the idea is to generate a small difference between the produced leptons and antileptons. But at 3 level, this doesn't happen. So because the rate of decay into leptons and antileptons for this Majorana neutrino is exactly the same. So I need to go to loop level calculations. And at loop level, new diagrams contribute to this decay rate that are specified here. And I obtain indeed an asymmetry that is characterized by this parameter is epsilon1 that is proportional to the difference in the rate of production of leptons and antileptons divided by the sum. So, and you see, this is a very simple quantity. So then that we can compute, and from here we can obtain the evaluation of the baryon asymmetry. Now, regarding numbers, so first of all, once I have the generated lepton asymmetry that is obtained by this decay of the heavy Majorana neutrinos, I can obtain what is the resulting B and L after considering all the different Faleron weak and strong Faleron processes that occur. And I obtain that approximately the final baryon number is equal to 1/3 of the original B minus L that it produced, that in this case is just the lepton number induced by the difference of the decay of the Majorana neutrinos into lepton and antileptons. So then, finally, so I can obtain from there what is the desired quantity that is proportional to epsilon1, as I specify here. Now, I have, of course, information about the neutrino masses and mixing angles that, as you know, come from the fit to oscillation experiments. But unfortunately, the Yukawa couplings that obtain a large energies, I control by additional quantities. First of all, this is a parameterization of this U-lept that appears here in the relation between the Yukawas and these 4 quantities that appear on the right. One is simply the Higgs vacuum expectation value. dm is the matrix of square root of masses, diagonal matrix of square root of the Majorana masses. The little m is simply the diagonal matrix of the square root of the masses that observe low energies. U-lept is what I compute from oscillation experiments, but unfortunately appears an arbitrary matrix R that is a 3x3 orthogonal matrix that contains unfortunate additional phases and angles that I cannot control, I cannot determine from Chow's oscillation experiments. Actually, if you do the calculation from the expression that I showed before, you obtain that the parameter epsilon1 is proportional to the masses that you measure at low energies, m little j, and proportional to the imaginary components of this mass and non-mass R. So then, and the parameter epsilon1 that has that is restricted, then is directly proportional to things that I measure at low energies, like M3 and M1, that are the masses, assuming hierarchy masses of the low energy neutrinos, proportional to this unknown Majorana mass M1 and divided by H0 squared. But from the one on epsilon 1 that I obtained before, I can obtain, since I know what M3 and M1 are from measurements, so I can obtain approximately a bound on M1. And M1 has to be larger than 10 to the 9 GeV. So the heavy Majorana neutrinos, assuming that there is no resonant effect, have to be heavy. And this is indeed the region of parameter space that you prefer, in this case, from standard leptogenesis. The mass of the heavy Majorana neutrinos have to be above 10 to the 9 GeV, and the reheating temperature, of course, has to be above this quantity. Now, let me emphasize that all the period formulas contain no dependence on ULEPT. However, it is well known that for temperatures as heavy as the one that we are considering, the tau lepton Yukawa are in equilibrium, and to obtain the symmetry, you need non-equilibrium processes. And when you introduce the difference of the Yukawa couplings of the different charged leptons, you obtain that a formula that is somewhat different and more precise than the one I presented before, that depends not only on U, so not only in R, but in U. So in the particular cases, R is approximately well specified if you assume a hierarchical spectrum, and everything suddenly depends on the mixing angles that I measure at low energy. So there are models, so specific models that contain the flavor information in what you can relate essentially what you measure at oscillation experiments to the asymmetry, but it's not a generic case. Okay, so the leptogenesis is somewhat related to the hierarchy problem because you know these heavy Majorana neutrinos induce quadratic divergences, quadratic corrections to the Higgs mass parameter. And actually, these are very large when you consider 10 to the 9 to 10 to the 10 GeV, such that you can invoke, one possibility is to invoke supersymmetry to address this problem of fine-tuning. That is a physical problem. It's not a real cutoff, but it's a real physical mass that appears. So then, and once you invoke supersymmetry, so then in any reasonable model, you induce also flavor violation in the lepton sector that can be measured at low energies. And I will not expand on this. So, and one additional prediction of this is the existence of Majorana masses that I can measure in a neutrino less double beta case. Now, the other option is to have baryogenesis at the weak scale. In this case, you generate an asymmetry at low energies, and you need to preserve it. So then if you generate this asymmetry at low energies, that you have to specify how it happens, the condition of preservation is simply related to the fact that the value that obtained at low energies is controlled by a double exponential behavior relation with the ratio of the energy of the Falaron to the T critical. That is essentially what appears inside the exponent is the ratio of the Hubble expansion of the universe compared to the baryon number validating rate. And in order to preserve, so the generated baryon asymmetry, you need that the Falaron rate is sufficiently suppressed, so you need that this energy of the Falaron is sufficiently large at the critical temperature, at the electroweak phase transition, where you are assuming that you generate a baryon number. And that implies that B over T should be larger than 1, because the energy of Falaron, as I told you, is proportional to the background expectation value of the Higgs. So establish a connection between particle physics and cosmology. In this case, that is related to weak scale. Now, that means the electroweak phase transition instead it has to be first order. You have to have a jump of B of the Higgs vacuum expectation value of the critical temperature. And this in principle can happen in the standard model. So you can study the effective potential at final temperature in the standard model and study what is the value of V over T at the electrophase transition. You obtain that this is controlled by this coefficient D that receives contribution from at one loop proportional to the sum of the couplings of all bosons and fermions square, but also is controlled by this trilinear coefficient E that receive only contribution from the bosons. So that means the gauge bosons. So in this particular case of the standard model, so you can compute what is V over T, and you can check what is V over T larger than 1 is related to E over lambda. Lambda is the quartic coupling that is related to a Higgs mass. And you obtain that there is no way that you can obtain a phase transition. The gauge bosons do not produce a sufficiently large correction. There is another problem that the separating sources are not high enough to produce variant asymmetry in the standard model. So essentially to make it work, you need first a modification of the Higgs effective potential to establish the first order phase transition, and also additional CP-violating sources. Now, the modification of Higgs effective potential is what is mostly studied because it's simpler, so it's only dependent on the Higgs sector at low energies. This can be modified in general by the addition of particles that couple to a Higgs that induce corrections to this parameter E that I said depends on the bosons of the theory, or can appear by a modification of the structure of the effective potential due to the presence of new scalars. These are two things. So in the past, for instance, I played back in the last century, so then we are playing with the possibility that stops induce a correction to E because they are bosons, they are strongly coupled to the Higgs, and they give a modification to E that could induce a large modification of the effective potential. So at final temperature, the problem was that that demanded very light stops. So if there's light stops, contribute to gluon fusion and also to Higgs to gamma gamma, and essentially an analysis, a careful analysis. So observe that the masses that you need that is representing these yellow bands. So then it had to be very light. So the stop had to be below 115 GeV to obtain a Higgs mass consistent with experiment. So then, and also let me mention that the left-hand square had to be very heavy. When we analyze what are the corrections to the Higgs processes, it turns out that they were unacceptably large. So you obtain corrections to the gluon fusion production cross-section that were factors of a few. That is totally inconsistent with observations. So this model is ruled out, but you can have additional models. For instance, in beyond the MSSM, you can have the NMSSM corrections, and in there you have additional couplings. You have an additional scalar, a singlet scalar that couples via coupling lambda to the Higgs doublets, and also there is a soft term associated that we call A lambda. So this is very nice that in certain limits you can make an exact analysis, assuming that the singlet is heavy, of what is the modification of Higgs effective potential. That is given by this V effective that I write there. I will not give you much details, but if you look at it, so then we have the first term that is simply the mass corrected by the temperature that gives a modification of the effective mass that pass from negative to positive values, as usually happens at high temperatures, producing the symmetry restoration process. But also the effect of the singlet, if it's heavy when you integrate out, is to produce essentially at tree level a modification of the effective potential. If you look at this expression that is in the middle, so and assuming that the mass is large, so simply gives non-renormalizable corrections to the potential. First, the simplest term is a modification of the quadratic and quartic term, so modify the quartic coupling. So, and actually can it render it negative, but then there is a sixth order term that makes it positive, and so on and so forth. Actually, if you do a precise analysis of this, so observe that when A over lambda is the quartic coupling over MS, A is a linear coupling that appears in this term, in this in this model. So when A over ms over lambda is larger than 1, it turns out that effective quartic becomes negative. And you can make a precise analysis of what happens in the theory. So, and it turns out that you can get indeed strong inverse phase transition, and is induced when there are large corrections, so to the effective potential. And this is a generic feature that happens, so you can make a generic analysis independent of any model. So where you consider all the corrections to the quartic coupling, to the high order terms, observe that the high order terms are suppressed by a certain cutoff that in the previous model was just given by the soft breaking term of the mass of the singlet. And you have modifications that are interesting in the triennial coupling. For instance, you can produce, so you can have a large modification of the triennial coupling of the Higgs that controls eventually the Higgs double Higgs production that can be tested experimentally. So then, for instance, you can see in this model, so the green and blue regions are regions of large modification. You can get the positive modifications of order a few. Unfortunately, that regions where you have positive modifications of the trilinear coupling that are represented here in this model by this ratio of lambda over lambda sm. So does not lead to a large modification of the production cross-section because of the particular dependence that we have on it. So it's still difficult to prove this model. There are many models, many simplified models that consider just singlets, the additional singlets in the standard model without any other doublet. They have been studied by different authors, and for the aim of time, I simply concentrate on a recent work by Marcela Carenas and Liu and Yikun Wang, where they studied this particular model with a singlet in situ spontaneous broken. And they demonstrated that in this case, just like in the other case, you can have a modification of the quartic coupling. So lambda due to higher operators, actually you can compute T critical and B critical associated with this. And you can therefore modify the depth of the potential. So then, this modification of the depth, so implies that the T critical is smaller, and at the same time you enhance B. So with a modification of the quartic coupling lambda, you produce both a modification of the depth, lowering T, and also you enhance B, so leading to large values of B over T that are required. And this model can be checked by double Higgs production. Indeed, there are large regions of parameter space where the singlet is, contrary to what I was analyzing before, is light, and you can have singlet production from the decay of the standard model Higgs, leading to 4B events that can be probed only partially by the high luminosity LHC. So then, and you can also have small modifications of double Higgs production that you can also eventually test as LHC, and this is different from what I had before. These are small modifications that can be eventually tested. I don't have time to expand on the MSSM because my time is essentially up. I just wanted to tell you that if you consider light, so light Higgses, you have another problem that you have to keep them in the analysis of phase transition. And you can have many different solutions where the vacuum differs from the standard model. And also in the transitions between different vacua, you can also have more complex transition that just the transition from 0 to V. And then one has to make a careful analysis of this to study if the transition happens, to study when the transition happens in nucleation. And we discovered in this analysis with Sebastian Baum, Marcel Carena, and Noshin Jia and Yikun Wang, we discovered that there are differences. It's important to concentrate on nucleation rather just to look at the transition temperatures. I didn't say anything about CP violation, and I will not say much. simply I want to say that when you have low energy CP violation that is connected to a Higgs, you tend to induce corrections to the electric dipole moments. So, and these corrections to electric dipole moments happen, for instance, in supersymmetry, induced by these separating phases, and have to be checked, have to be considered with carefully, and are very dangerous. So that, I believe, is one of the most important constraints on the realization of electric baryogenesis. So to be sure that whatever you add, when you generate the baryon asymmetry, you don't violate the electric dipole moments. And in particular, in the case of the case of supersymmetry, you can generate a baryon asymmetry by adding the separating phases to the Deisino masses, but you have to be very smart and do it only to the Vino. If you add a phase to the Wino, you will be in trouble. And I know that the organizers want me to end. So let me just mention that there are ways of relating the dark matter density to baryon density, and let me conclude. So my conclusion is the origin of the matter-antimatter symmetry is one of the fundamental open questions in particle physics and cosmology, and is as important or more important than the problem of dark matter. Several proposals exist for its dynamical generation and lead to very difficult physical phenomena, as I explained. The resolution of this question will involve experiencing high energy intensity cosmic frontiers, and of particular relevance are Majorana neutrinos and also the electric dipole moments that controls these two scenarios that I discussed. Collider physics is already constraining some of the scenarios. I show you electric baryogenesis in the MSSM is constrained and ruled out. And the relation between baryon and dark matter contributions to energy budget may be a clue towards the resolution of this puzzle, but it's still an open question. Thank you very much.
Okay, thank you, Carlos. We have no time to ask a question. Okay, we may discuss sometime later. Okay, thanks, Carlos. Thank you all speakers for this session. Okay, let's end this section.
Thank you, and again, sorry for the late connection.
Okay, okay.